I shouldn't say conditioning on n events. Probability of intersection of n events. So this is a generalized version. By all means, you know, some people would say Bayesian statistics would sort of eventually end up in being frequent statistics. Yes, it is possible, depending on, you know, what happens with the conditioning. Suppose you have n different events, A1, A2, all the way up to AN. And we want to find the probability of the intersection of all the events. In other words, I want to find the probability A1 and A2 and A3 and A4 and A5 all the way up to and AN. If they're all independent, this probability is easy. Do you agree? You just find the individual probabilities, multiply them together, we're done. That's not the case here. We're going to say the events A1, A2, dot, 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 AN, and they're not independent. This sort of works nicely using Bayes rules, assuming we start at A1. So it would equal to the probability of A1 multiplied by the conditional probability of A2 given A1. Yes, that should make sense because that's just, you know, the rule that we had for conditional probability. Now, multiplied by the probability of A3 given A1 comma A2. Yes. Multiplied by the probability of A4 given A1, A2, A3. Yes.
So the A1 comma A2, is that kind of saying the probability of A3 given the probability of A2 given the probability of A1?
No, I'm going to explain that with the case 3. And it will go all the way up to the last one, probability of AN given A1, A2, dot, 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 A in minus 1. Seems very painful, right? It is very painful. For case 2, this is obvious, easy. For case 3, it might seem weird. So probability of A1 intersect A2 intersect A3. Let me call that B. So I can write this as probability of A1 multiplied by the probability of B given A1. Yes?
Yes. Yeah.
Probability of B given A1 is the probability of B, well, let me write it this way. Probability of B would be probability of A2 intersect A3. Yes. And so this would equal to, how do we do that? Probability of A1 intersect A2 intersect A3 divided by probability of A1, right? You can switch the order. Let's see, how do we do this? So when we condition on A2 intersect A3, that conditioning will apply to A2 as well as A3, because this is the evidence we are bringing into A2 and A3. So when I condition on A1, I'm applying the condition to both A2 and A3. So I can write this part as probability A2 multiplied by probability of A3 given A2 without the conditioning, right? But whatever information that we bring in here is going to apply to that as well as that, correct? So if we go back to our problem, what is the probability that Martin brought a red dye the first time and a blue dye the second time? The conditioning, given that he heard a 2 and a 4, will apply to both of them, yes? So this conditioning is going to apply to that as well as to that. So this would become, or I should not have erased this, not there. Without the conditioning, but if I bring that A1 in, because we have the condition, we'll end up having probability of A2 given A1 multiplied by the probability of A3 given A2, comma A1. You can write this all the way up to AN if you want, if you've got too much time in your life, but it's not necessary. Now, there is a thing called state space models and hidden Markov models. Those are simplified if the previous state, or Markov models, if the previous state, the current state depends only on the previous state. That's what we call a Markov property used in hidden Markov models. In other words, whatever happens at A2 will only depend on A1, A3 will only depend on A2, A4 would only depend on A3, and so forth. That's a simple case, and that's Markov property, but there are plenty of other cases that use this.